Okay, so the Michaelis Menten equation, special case 1. So when the substrate concentration is very low, it's a lot lower than Km, V0 equals V max times S over Km. And that's the equation you'll use when the substrate concentration is really a lot lower than Km. Now, why is that? Well, let's look. So we have the original Michaelis Menten equation, right? So we have V0 equals V max over substrate concentration, and then Km plus substrate concentration, right? So let's say Km is 1000 and substrate concentration is 1. Well, if you do the math, right? So for example, if we have both of these as 1, V max is 1, substrate concentration is 1. Well, 1 divided by 1000 and 1 divided by 1000 plus 1 is not that different. So it's almost negligible. And so because it's so different, right, because substrate concentration is so much lower than Km, you can basically disregard the substrate concentration. And so the actual equation for this becomes V0 equals V max times substrate concentration over Km. So that's why we can get rid of substrate concentration, because it basically doesn't matter at that point. And you can do the math, and the difference is very negligible. So the rate is directly proportional to substrate concentration and is for first order. Okay, so the special case number 2. So at high substrate concentrations, where substrate concentration is a lot larger than Km, V0 equals V max. So why is that? Well, once again, we have the original Michaelis Menten equation. So if we say that substrate concentration is 1000, right? It's 1000 and Km is 1. Once again, the same logic applies. It's so large of a difference that the actual math, the answers differ very mildly, and so therefore you can disregard Km in this instance. So if you disregard Km, well, what are you left with, right? You're left with V max multiplied by substrate concentration divided by substrate concentration. Well then, since everything's multiplying, you can actually cancel these out, and so initial velocity will equal V max. And so rate is maximal and is 0 order because it's independent of substrate concentration, right? Because see, in this final equation, there's no substrate concentration, so therefore it's independent, and that's why it's a 0 order equation. Okay, so the special case number 3 is when substrate concentration is equal to the Km, V0 equals V max divided by 2, right? So let's look at why. So you have the original equation, and so what happens is if you say that S is equal to Km, right, the numbers are the same, well, basically you can make Km another S, right? So if you make it an S, well, S plus S is 2S. So remember that you can cancel this, right? You can cancel the numerator and the denominator, and so once that's canceled, all you're left with is V max over 2 is equal to initial velocity. So that's how you get that. And so Km is equal to the substrate concentration, where reaction rate is 1/2 the max reaction rate. So the significance of Km, since we've been talking about it so much, is it's independent of enzyme and substrate concentrations. And the biggest, I think, importance of Km is that it can be used as a measure of substrate affinity, right? How much does the substrate like the enzyme? So Km is equal to the concentration where half the active sites are filled, right? And that was shown right here. Because Km, when Km is equal to S, it's shown when half the it's half, because V max is the total number if all enzymes were filled, right, with the substrate. So Km is equal to the concentration where half the active sites, half the enzymes, are filled with substrates. So let's go into this a little bit more. We have, right, enzyme plus substrate. The forward reaction is K1 equals ES. Backwards reaction is K minus 1. So in this case, if we assume that K minus 1, right, the reverse reaction is a lot larger than K2, then we can assume this, right? Because remember, the big reaction is after this we have ES and then K2, and then you have E plus P. But over here, we're assuming that K minus 1, right, K minus 1 is a lot larger than K2. And like the logic I was telling you, if it's the difference is so much, and if it's addition, then the answers won't differ that much, and therefore you can basically disregard K2 in this instance. So therefore we can assume the Km is equal to K minus 1 over K1, right? Because this was the original Michaelis constant, and because we're disregarding K2, we can assume this is Km. So Km is equal to this, and so this is the equilibrium dissociation of the constant of ES, right? Because this is the new equation. And based on this, we can say that a low Km is high affinity and a high Km is low affinity. So why is that? Well, the forward reaction is K1, right? And so we want that one to be a lot larger. Because if that's a lot larger, that means that the reaction is pushing towards ES, and that means that the enzyme and substrate really want to stay in this position. If the K minus 1 was larger, it would mean that it's pushing the reaction this way, and that this would be larger. But that's not what we want, right? Because we want the affinity to be higher. We want the enzyme and substrate to stick together more. And so we want Km to be larger, K1 to be larger. So over here, so if we have K minus 1 and over K1, well, if K1's larger, right, the forward reaction, and that's a 2, well, 1/2 is going to be smaller than the reverse, right? And so 1/2, the lower Km, is going to have higher affinity because K1 is associated with the forward reaction and it's larger. And so therefore the lower number will actually have higher affinity. Okay, and so the going over to the next concept is turnover number. So turnover number is the number of substrate molecules converted into product by an enzyme per unit time when the enzyme is fully substrated with substrate. So turnover number is just Kcat, which is equal to K2, if you remember in my earlier videos. So Vmax is equal to Kcat times E total, okay? Moving on, Vmax is proportional to the total enzyme concentration, ET. The only way to increase Vmax is increase the total number of enzymes. And that makes sense, right? Because the only way to increase the total is just to add more enzymes, because you've already reached your max. Like, it's kind of like if you had a car and you're pushing it to the max limit, well, you have to upgrade the engine, right? In this case, you have to increase the number of enzymes to increase the potential Vmax. So why is this important? Well, Vmax can be used as a measure of enzyme concentrations. This is clinically important, right? It's not just fun to know, but it's clinically important in medicine, where you can measure liver function and heart disease based on this Vmax. So another concept we have to talk about is significance of Kcat over Km. So this actually measures the catalytic efficiency. So Kcat, right, is the turnover number rate of catalysis. Km is the strength of enzyme-substrate interactions. So for the highest catalytic efficiency, we want Kcat to be a large number, as large as possible, right? Because that means the turnover rate is very high, and we want Km to be as small as possible. So we want the strength of the enzyme-substrate interaction to be low. And that means the highest catalytic efficiency. Okay, because remember how I said that a lower Km is a stronger, it has a higher affinity. Okay, so Kcat over Km can measure substrate preference, right? And then the fastest enzymes, right, the fastest theoretical possible enzymes, approach the diffusion limit of 10 to the 8th or 10 to the 9th, which is pretty fast for an enzyme. And another useful trick for the Michaelis Menten equation is to change it into this format, the double reciprocal. This is important because if you get into this form, you can use this equation, right? And that should be familiar, because this the m represents the slope, the x is x, and then b is the y-intercept. And that's useful for when you graph the Michaelis Menten equations, and they're easy to spot differences. Over here, how we get this equation from the original, Well, all I did is flip them, right? So 1 over V0, and then flip this. So Km plus S is on the top, right? This was on the bottom, and then Vmax is on the bottom. Over here, it's on the top. Okay, so how do you get into this form? Well, just since it's addition on the top, split it up into Km Vmax over S plus S over Vmax S. And so since there's S on the top and bottom, these cancel out, and you are left with 1 over Vmax. And then you can split it up, because this is multiplication on the bottom, into Km over Vmax multiplied by 1 over S plus 1 over Vmax. And so that's how you get this equation. So in the next video, I'll talk about enzyme inhibition. And thank you for watching, and I hope this helped.